Okay, so I think I should start on the second tutorial. Okay, so I'm Jia Krishna Chinavtar. Uh, I'm going to a TA for this NPTEL course on variational calculus and its applications in control theory and nanomechanics. So this is our second tutorial session. It's February 14, 2023 today. Okay, so let me begin with the overview. So in today's session, I would be discussing, I would be reviewing the concepts that we had discussed in the previous tutorial sessions, especially the basics of, the basics of variational calculus. Then we would be continuing a brief discussion on generalization of Euler-Lagrange equations. Thereafter, I would be reviewing the concepts of the techniques used for obtaining numerical solution of Euler-Lagrange equations. Thereafter, I would be following the discussion with a good number of solved problems in all these different aspects of variational calculus that which are to be covered in today's session. Okay, let me begin with the review of the basics of variational calculus. So as you recall from the previous discussion, that optimization, that variational calculus is essentially optimization in function space. In this, the the extremum of the functional is unlike the usual optimization. Here we actually uh, we actually solve for a function which tends to minimize or maximize some cost function, or what we call in here as a functional. So we start with a very basic functional, which is, say, j of y, and it's defined as integral over x1 to x2, which is a domain, and we will be discussing fixed domain right now. So here it's over a fixed domain. It's over a fixed domain. x0, x1 to x2. So the integrand is is a function of x, y, and y prime. Now upon extremizing jy, this leads us to the Euler-Lagrange equations, which is given by d by dx of del f by del y prime minus del f by del y is equal to 0. This is essentially the necessary condition for obtaining extremum of a function, and this is also known as Euler-Lagrange, as you already know about this. Now let's go to the generalization of Euler-Lagrange equations. We know that in many scenarios, we won't have such a simple looking functional as j of y of where the integrand of the function is just a function of x, y, and y prime. In mechanics and in various other areas of engineering and maths, what we say is the function can contain either higher terms of higher order derivatives, the extremal y, and for the case we have discussed, we see that it's just a function of single independent variable, which is x. But it may also be possible. It's seen that there can be multiple independent variables also. So this we broadly so in the section on generalization of Euler-Lagrange equations, we just broadly have three different cases as of now. The first is the case where the functionals contain higher order derivatives of extremal, and higher here implies that the derivative of the extremal is 2 and more. So in this case, we have the general expression for our functional as j of y is equal to x1 to x2, the integral over x1 to x2 of the integrand, which is a function of x, y, y prime, y double prime, and it could go up to nth derivative of y. And mind you that this is again defined over a fixed domain, and which is the interval x1 x, which is which whose limits, the domain whose limits are x1 to x2. Now, when extremizing the above this particular function, it leads us to a generalized Euler-Lagrange equation, which we call as which we have here as -1 to the power n, the nth derivative of del f by del the partial derivative of f with respect to yn, plus minus n to the power n minus 1, then n minus 1th derivative of the partial derivative of f with respect to with respect to yn minus 1, and it goes till we have plus f del f by, sorry, dou f by dou y is equal to 0. And then we have the second case. In the second case, we have functionals which contains of several dependent variables, but it still contains just one independent variable. Now, a very typical example or typical expression, or the standard expression, so to speak, of the functional would be j of q vector is equal to t1 t0 to t1 l of t q vector comma q dot vector dt, and here we have q vector is defined as it's a vector whose components are q1 q2 till qn, and mind you, all these components are a function of t. In this case, when we upon extremizing with respect to every component of the set of dependent variables, which is q vector here, we have the Euler-Lagrange equations are essentially a system of n second order ODEs, and it is given by d by dt of dou L by dou q dot I minus dou L by dou qi is equal to 0. And here I runs from 1 to n. So essentially we have one equation for every component of the dependent variable vector q. Now let me proceed to case 3. So in case 3, we have it's about functions containing two or more independent variables, but right now in our discussion we'll be just considering two independent variables. Here it's we have a standard expression for the simple functional in containing two independent variables, and it has just first derivatives of the extremum or extremal u. Now the integrand of this functional is f function of x, y, u, ux, uy, and ux and ui are essentially the x and y derivatives of the extremal u. And we just represent del u by del x as p, and del u by del y is equal to q. Now extremizing j, or the functional here with respect to u, it leads us to the following EL equations. So the equations here is dou by dou by dou x of dou f by dou p plus dou by dou y of dou f by dou q minus dou f by dou u. And the functional containing higher order derivatives of u, the higher order derivatives of u, for such functionals we have an expression here, and again I have just for the sake of simplicity I have considered derivatives of the extremal u to just to up to second order derivatives. So the corresponding Euler-Lagrange equation we have is del f by del it should be u actually, del f by del u, or dou f by dou u minus dou by dou x of dou f by dou ux minus dou by dou y of dou f by dou u y, plus the second partial derivative with respect to x of dou f by dou u double x plus second derivative of uh, f with respect to x and y successively of dou f by dou u xy plus second derivative of dou f by dou u double y with, with respect to y is equal to 0. Okay, so with this, in these two slides, I have discussed the three cases of the generalization of Euler-Lagrange equations. Now let me proceed to just discussing a bit on numerical simulation of Euler-Lagrange equations. In this, the technique, we'll be discussing three techniques as was discussed in the in the in the week 3 of this course. So the first technique is Euler's finite difference method. So let's start with a very basic functional, which is f of y is equal to integral over a to b of the integrand f of x y prime over x subject to ya is equal to y naught and yb is equal to yn. So these are the two boundary conditions. Okay, so what does this technique say? So essentially, this technique states that, or this technique invokes the it follows from the very way we define derivative. So you must be knowing that the way we defined a derivative, say if I define y prime, it is defined as limit of y of x plus h minus y of x divided by h as h tends to 0. So we have an infinitesimal quantity h. So we take the values of this function y at 2 points, at x plus h and y and x, and then take its difference and divide by h, and then we the value of this expression as h tends to infinity gives us the first derivative of y. Okay, so but what we say is this gives us the expression for derivative that we often see in calculus. But from a numerical perspective, we may not have an exact, so to speak, the derivative of this function, or the thing is we would like to, or if I take back my words, so essentially what I'm trying to say is I don't want h to go to 0. I just want h which is small quantity, just a small quantity, small but not infinitesimal. So in this case, what I'll do is I will just take, say, something of, I'll just replace x as something like x plus delta of x minus yx by delta x. Now this delta x, and I'm just going to take it to be some small quantity. Mind you now that in this way we are expressing our derivative of y, but this is no longer exact but just approximate. So this is just approximate value. So this is how we are trying to approximate our first order derivative of y. So this is what we call as finite difference methods, or finite difference scheme of to obtain an approximation for derivatives. Okay, so what we do is in this functional here, which is f of y is equal to a to b of f x y prime dx. Now what we do is we will tend to first discretize our domain. Now the discretizing of domain implies that we are essentially just uh, instead of considering the entire domain and defining a function over the entire domain at every point within the domain, we are actually, our aim is just to find our values of the extremal y at certain locations. So these are the locations x0, x1, x2, xi till n, till xn. So which means before I mean, over this interval x naught to so over the interval a to b, we had infinite points, but now we are essentially but now what we are doing is we are just finding, we are just taking the values in the domain at certain points, which are also called as grid points. So x naught, x1, x2, x3 till xn are all grid points. Over this we tend to approximate, over this we tend to approximate our first derivative of y. Okay. Okay, so let's go back to our expression here again. So we have f of y, and the integrand is f of x y prime, isn't it? Now what we do is, let's just take it to be, let's just substitute the values and convert this integral in terms of a summation. I'm sure you have learned about this back in your high school days, of approximating as integral to a sum, or and vice versa. And going from sum by taking delta x to be very close to zero, then it becomes an integral again. And then in this integrand, we put the value of y prime in terms of its approximate value, which is delta yi by delta x. Now, and this gives us, so this gives us a function. So the function of y has become a function in terms of y naught, y1, y2 to yn. And mind you that y naught, y1, y2, these are the values of the extremal y at the grid points x naught, x1, x2 till xn. So essentially what we have is, after approximating the function in the integrand, we are left with a variational problem, which has been converted to, or which has reduced to, a standard multivariate optimization problems. And if I ask you how many variables there are, then there are n plus 1 variables. Now you'll say, what are the n plus 1 variables? They are nothing but y naught, y1 to yn. So these are our n plus 1 variables. And then we use the tools from the optimization theory, wherein we first find the necessary condition, which entails that the derivatives of the resulting function with respect to each of the components y I is 0. And but in this case, I will be taking derivative of f bar with respect to y only for I is equal to 1 to till n minus 1. I will ask me, okay, fine, where has y naught and yn gone? Okay, now if you go back to the previous slide, then you will see that actually these are the values at, so these are the values here. This is the first boundary condition, and this is our second boundary condition. So which means at the either ends of this discretized domain, we already know our value of y at those 2 points. So that's why we have left out. We did not carry out the first derivative of taking the first derivative of the cost function, or or the function here of f bar with respect to yi's. And after equating this every partial derivative of respect to yi's to 0, we will have essentially a set of n minus 1 equations. And what we do is we'll tend to, and what we'll do is our process, essentially our task is to solve those n minus 1 equations and to obtain our yi's. So yeah, so this means that we have obtained an approximate value for our extremal, but whose value are only present at all the grid points for the domain. Okay, now let's go to the second technique. The second technique is called as Ritz method. Now in Ritz method, our the way we will carry out this or we will try to implement this Ritz method is, first we will approximate our variable y using a family of linearly independent functions phi I, which goes from I is equal to 0 to n. So essentially we have n plus 1 linearly independent functions. And the set of these linearly independent functions is also called a basis. And I am sure you may have heard of this particular term called basis if you have studied linear algebra. In this, we often tend to say a set of uh, functions using which we can span an entire vector space. So that's what we call as a basis. Okay, now what we do is we have a variable y of x and we want to approximate it in this set of basis functions or in this set of independent functions phi i's. So what we'll do is, okay, we have y of x and it's approximately equal to y(n) of x, and this is defined as, or this will express it as phi naught of x as a function of x plus c1 phi 1 x plus it goes up to c1 phi n of x. Okay. Now herein we also need to figure out a way as to, and even our basis function has to satisfy certain conditions. The first condition is, or the one of the condition is that we will choose phi naught of x. So the choice of our phi naught of x should be such that it satisfies the boundary conditions y of a is equal to ya and y of b is equal to yb. And the other basis functions, which are phi I for I is equal to 1 to n, it has to satisfy the homogeneous boundary conditions phi j or at a is equal to phi j at x is equal to b is equal to 0. So these are so our basis functions must meet these two conditions or criteria. Okay, then now our next step is to substitute the approximation in the functional. Now you must already be very familiar with our functional, what I'm talking about. It's this functional which you are already very familiar of. So this is our function. In this functional, we are substituting the approximation for y. And this leads us, so after putting that and integrating over the domain, we are left with a standard multivariate minimization problem, wherein we need to determine CIs or the constants, or so to speak, the coefficients of the approximation for y of x. Now, since we have a standard multivariate minimization problem, all we need to do is solve for CIs. So that's our step. And this has to be done by setting the partial derivatives of fn with respect to CIs to 0 for each of the CIs. So once we obtain CIs, our step is, then we already have what we wanted. We have CIs, we can put it back into the expression here, as I have in the expression here, and get an approximate value for, or approximate expression for y of x, or the extremal. Now let me also talk about the third technique in this set of methods to solve or to obtain numerical solution of Euler-Lagrange equations. So in Kant, so this is the method called as Kantorowicz method. Now suppose our suppose our dependent variable is a function of x and y, and I'm sure you may have seen such cases wherein we have one independent variable so one dependent variable in terms of two independent variables. And in this case, what we do is we again approximate our extremal, which is z here, in terms of some series expansion. So there is a series expansion is phi naught of xy plus summation of I is equal to 1 to n ci is a function of x phi I xy. Okay. So again, we have to make proper choice for the basis functions. And mind you, these are again basis functions. Phi naught, phi 1, phi 2, all these are basis functions. So they again have to satisfy certain conditions. So the first condition is that phi naught of xy, it has to satisfy the boundary conditions over the, which is defined for the particular problem. And the rest of the basis functions, which is phi of xi, y, they have to satisfy homogeneous boundary conditions. So homogeneous boundary conditions implies that it has to have, that all these basis functions has to have a value of 0 at the boundary. Okay. The next step in this in our procedure is that we would be approximating our integral, or which happens to be our function f of zn, and we have substituted the approximate version, approximate expression for z, which is zn, in this function, or taken as the argument of this function. And this is defined over a domain omega zn xy dy by dx. Right? We substitute the expression here of zn xy, and then we carry out, rearrange it, and then carry out, and so to speak, we express it in, a, in an integral over y. And we see here also there's integral over y, and the rest are also integral over y. And after carrying out the integral with respect to y, we are left with an inner integral. After carrying out the integral with inner integral with respect to y, so we will have an expression solely in terms of x. So essentially, we will have the expression for our function will become, the integrand becomes just a pure function of x. Now we essentially have a Euler-Lagrange equation, a variational problem in a single independent variable x, and we can apply the usual or the standard Euler-Lagrange machinery. Just you very well know what we mean by that. What we mean is we will take the extremize with respect to the variable, principal quantity here, and then obtain our Euler-Lagrange equation and solve it to obtain our solution. Okay, so with this, I have completed the review part, or theory review, or a review of the theory for tutorial session 2. So we started with reviewing the basics of variational calculus. We were just summarizing briefly of what we had discussed in the first tutorial session. Then we have studied generalization of Euler-Lagrange equations for 3 different cases: case 1, case 2, and case 3. And so case 1 was functions containing higher and 2 and more derivatives of extremal. Case 2 contains functions contains several dependent variables but one independent variable. And case 3 is functions containing 2 independent variables. The third is we discussed about 3 techniques, which are which have been used to obtain numerical solution for Euler-Lagrange equations. Okay, now let's start solving a bunch of problems in for all these different topics that we have just discussed. Okay, let's start with the first part, or the first set, which is basics of variational calculus. Okay, so we have a question, which is to find the extremal of the functional g of y over a to b y square minus y prime square minus 2y cosine hyperbolic x of dx, integrate over dx. Okay, now let's solve it. So what would be our first step? First step is we have this as our function. This is our function, or the no, this is our integrand of the function. We'll just call it f of x, y, and y prime. So the first step is to determine the Euler-Lagrange equations. Euler-Lagrange equation, because we are going to have just one equation. This Euler-Lagrange equation is determined by, is defined, or expression for which is d by dx of the first derivative of f with respect to y prime minus del f by del y is equal to 0. Okay. Now we take the first okay. Now we take the first partial derivative of, or the partial derivative of f with respect to y prime. If we look closely at the integrand, it is the first derivative of f with respect to y prime is minus 2y prime. Then we have del f by del x, del y is defined after getting out the derivative operations, the differentiation operation. We have del f by del y as 2y minus 2 cosine hyperbolic x is equal to 0. So this implies that taking first derivative of the derivative of y prime with respect to x, we have minus 2y prime minus 2y plus 2 cosine hyperbolic x is equal to 0. Factoring out 2 and then just rearranging our x equation here, we have y double prime plus y is equal to cosine hyperbolic x. So this is our equation, or this is our extremal. But mind you that this just gives us a differential equation. So this gives us a differential equation for the extreme. It doesn't directly give us extreme, it just gives us a differential equation. We can solve it again. You know very well that this equation is a second order linear non-homogeneous ordinary differential equation. So it means the solution will be expressed in terms of the homogeneous solution and a particular integral. I won't solve it. I think we had discussed it in great detail in our previous tutorial session. And if you would like to really understand it, please you could just refer to the first tutorial. Okay, now we'll solve a bunch of problems in this basket of generalization of Euler-Lagrange equations. Okay, so the question asks us to find the extremals of the functional g of y of x, z of x is equal to 0 to pi by 2, y prime of y prime squared plus z prime squared plus 2yz. And this has to be, the extremal has to satisfy boundary conditions which are y is equal to 0, at y at 0 is equal to 0, and y at pi by 2 is equal to 1, and z of 0 is equal to 0, and z at pi by 2 is equal to 1. So what should be our step? So I mean, so are you able to identify which case this belongs to? So this is a case wherein the functional consists of two dependent variables, but just one independent variable. So the two dependent variables are y and z, and the only independent variable is x. Okay. So the Euler-Lagrange equations, we'll have a set of Euler-Lagrange equations. Since the number of dependent variables are 2, we will have two Euler-Lagrange equations. The first one will be dy by d of dx of say I call the integrand here as f of y z is equal to y prime squared plus z prime squared plus 2yz. So dy by dx of del f by del y prime minus del f by del y is equal to 0. And the second Euler-Lagrange equation is dy by dx of del f by del z prime minus del f by del z is equal to 0. This implies that d by dx of dou f by dou y prime is 2y prime minus dou f by dou y is 2z is equal to 0. Likewise, we'll have so x. So dou f by dou z prime is 2z prime minus 2y is equal to 0. The first Euler-Lagrange equation is after factoring out 2, we'll have y double prime minus z is equal to 0 and z double prime minus y is equal to 0. Okay, so we have coupled equations, coupled equations in y and z. but we would like to obtain just once, if we could have an ordinary differential equation in just one independent variable, that would be very convenient for us to obtain a solution. So what we do is we take this to be 1 and this to be the second equation. We differentiate 1 with respect, differentiate 1 twice with respect to x. This gives us y. It's y is already the first term is already a second derivative of y with respect to x. Now, if we differentiate it twice with respect to x, we are left with fourth derivative of y with respect to x, and minus z of z double prime is equal to 0. Now, from the second equation here, we have z double prime is minus y is equal to 0, isn't it? So what we do is we substitute this y, equation 2. So then we are left with 1 minus y is equal to 0. Now this is an equation, fourth order linear homogeneous ODE. I won't solve this in detail because anyone who may have attended the first tutorial session will will have already known how to solve this, because we had discussed solving this fourth or linear homogeneous ODE in greater detail. I'll just take the final solution, or the final expression here, which is of the solution as y of x is equal to a cosine hyperbole x plus b sine hyperbolic x plus c cosine x plus t sine x. Now, to obtain the expression for z, what we know from our first equation is y double prime z is equal to y double prime. So we have z of x is equal to y double prime of x. Now let's consider every term. Let's derive an expression for zx by by applying the second differentiation operator on every term in the expression for y. So the first derivative of cosine hyperbolic x is sine hyperbolic x, and second, after applying the differentiation operator again, we have cosine. We get back our cosine. So the first term is nothing but cosine hyperbolic x. Likewise, the first derivative of sine hyperbolic x is cosine hyperbolic x. After performing a differentiation operation again, we have sine operation, sine hyperbolic x. So we just have then plus the first differentiation, the first derivative of cosine hyperbolic x is minus sine hyperbolic, and the second is cosine. So it will be minus cosine hyperbolic cosine x. Sorry, so cosine x. So it is minus c cosine x. Likewise, I'll not put. Okay, the first derivative is sine x. Sine of sine x is cosine x. Second is minus sine x. So we have minus t. Okay, fine. Now, if we look carefully at our boundary condition, what we see is y of 0 at 0 is 0, and y at pi by 2 is 1. And for even for z, it is z of at 0 is equal to 0, and z at pi by 2 is 1. Now, if what we can conclude from the after having a look at the boundary conditions, that the boundary conditions for y and z happen to be the same. So what do we conclude here? What we conclude here is, if the differential equation, again, uh, I'll just do something. I'll just differentiate equation 2 twice with respect to x, and then substitute y double prime is equal to z. So we also have minus z is equal to 0. So if we have the same boundary condition and the same differential equation, we should have the same solution, isn't it? Yeah. So when we let's take a look at the expression for y of x and z of x. Okay, the first term, which is a cosine hyperbolic, is the same. B sine hyperbolic is the same. But from the third and fourth onwards, for the third and fourth terms, we have plus is takes a form of minus and in both the terms. In order for both the solutions to be equal, what can you conclude? Since y of x is equal to sine of x, sorry, is equal to z of x, this implies that we have to have something known as, we have to have the same expressions here for both y and z. So for this to happen, we must have c is equal to 0 and d is equal to 0, isn't it? So it's c is equal to 0 and d is equal to 0. Fine. So this is our first conclusion, that y of x is equal to z of x. And this has to be because same, I will call it same differential equation or same ODE and same basis must lead us to the same boundary conditions, to the same solution, isn't it? This follows from our uniqueness theorem, which we won't be discussing here. Okay, so we are left with y of x implies that y of x is equal to a cosine hyperbolic of x plus b sine hyperbolic of x. Okay, now let's put our boundary conditions. So BCs are y of 0 is equal to 0. So this implies that you know very well that cosine hyperbolic x at x is equal to 0 is 1, and sine hyperbolic of x at x is equal to 0 is 0. So essentially it is a is equal to 0. Now let's apply our second boundary condition, which is y of pi by 2 is equal to 1. So this implies that a is already 0, so nothing to worry about here. And this we have as b sine hyperbolic pi by 2 is equal to 1. So this implies that b is equal to 1 by sine hyperbolic pi by 2. So therefore, y of x is sine hyperbolic of x divided by sine hyperbolic of pi by 2. So this is our solution. Okay. Now let's take a look at our second problem in this series. Okay. Now it asks us to find the extremal of the functional j of y is equal to 1 plus y double prime squared, isn't it? Over dx. I mean integrate over dx. So integrated over x is equal to 0 at x is equal to 1. And our extremal must have the boundary conditions, y of 0 is equal to 0, and the others. Okay, let's start with our solution. Is we will start with, first we have to obtain our EL equations. So this is a functional. The integrand of the functional consists of a second derivative in y. So we have it as a the expression is a dy. So I'll call the integrand again as f. So it is f by del prime minus dy dx of del f del prime plus del f by del y is equal to 0. Okay. What we can clearly see from our functional, from the integrand of the functional here, or from the expression of f, is it's a function of just y double prime. So this means that we'll have del f by del double y double prime is 2, and dy by dx is 0. Similarly, del f dou f by dou y is 0. So we are left with 2y fourth derivative is equal to 0. Factor out 2, I have just fine. So to obtain the general expression for y, we need to integrate it 4 times, isn't it? So we'll first integrate y4 with respect to x 4 times. In succession, isn't it? One after the other. So upon integrating first, we have the after the first integration we have y. I'll just write it as like this. There's nothing but some constant. We'll call it a. Integrating it twice gives us ax plus some constant b. Mind you, a and b, all these are all constants in sequence. And the third after performing the third integration, we have ax squared by 2 plus bx plus we have one more constant, which is c. Let's integrate the fourth time. We have y of function of x is equal to ax cubed by 3 into 2, which is 6. And likewise, we have bx squared by 2 and plus d. Okay, so the general expression for y says that we have first we need to find the particular solution. We need to determine the values of a, b, c, and d. Okay, but haven't we already been given an expression for? We have already been given an expression for our function here, or or sorry, we have been given the boundary conditions. Okay, so let's apply boundary conditions. So y of 0 is equal to 0. This gives us, we will have t is equal to 0, isn't it? The second equation is y prime of 0 is equal to 1. So y prime is dy by dx. So from this we have c is equal to 1. Fine. And the third boundary condition is y of 1 is equal to 1. So then this means that t is already 0, so c is 1. So we have a by 6 plus b by 2 is equal to how much? Plus c actually is equal to 1, isn't it? And the fourth condition here is the fourth boundary condition is, or it's c is all we already know it's 1, so let's put 1 here. And what we see from here, 1 goes away, so this leaves us with, and multiply throughout by 6, we have a plus 3b is equal to 0. And the fourth condition is y prime of 1 is equal to 1. This means that a by 2 plus b plus 1 is equal to 0. And what we do here is we'll just have a plus 2b is equal to how much? Minus 2. Okay, first we substitute, what we'll do is this gives us a is equal to minus 3b. Substitute heat here, we'll have minus 3b plus 2b is minus b is equal to minus 2. This implies that b is equal to 2, and this implies that a is equal to minus 3 into 2, which is minus 6. Okay, so our expression is y of x is equal to minus 6, isn't it? Minus 6 into x cubed by 6, so it is minus x cubed plus x squared, isn't it? Because 2 cancels out, plus c is 1, which is fine. But we need to verify it. Let's not take anything at its face value. Let's just check whether it fulfills the boundary conditions. So y of 0 is equal to 0, fine. Yeah, that's trivial. Y of prime is equal to 1. Yeah, so it becomes minus 3x squared plus 2x at 0. So we have 1, right? That's true. Y of 1 is equal to 1. So 1, so it's minus 1 plus 1. So 0 plus 1. Yeah, so it gives us, it's right. And y prime is equal to 2x is equal to 1 is 1, fine. So it's minus 3x squared plus 2x plus 1. So here is something, it's not adding up here, isn't it? So we need to verify this, because it seems that this gives us minus 3x squared plus 2x, so it's minus 1 plus 1, it gives us 0. Okay, so we need to just look at our boundary conditions here, whether we have actually done it right. So y of 1 is a by 6 plus b by 2 plus cx is equal to 1. Fine, that's true. Okay, yeah, I have made a mistake here. It's mistake here. So 1 cancels out actually, yeah. So 1 cancels out. So we have 0 here. And but what we clearly see from here is it gives us a very trivial solution, isn't it? It gives us a trivial solution. For substituting, there's b is equal to 0, a is equal to 0. So it's a is equal to b is equal to 0. So which means that we have a 0, b 0, d 0. So we have just c into x. So c is 1, so it's x. Okay, whether it satisfies the boundary conditions, yeah. Y is 0, fine, that's true. Y prime of 0 is 1, yeah. 1. Y1 at 1 is 1, right? Y prime of 1 is 1. So these are solutions. It's a simple solution. It's just straight line passing through the origin, right? Yeah. Okay, now we have our third problem in line. And this problem asks us to determine the extremal of the following function. And the functional is j zxy, and it's a double integral over the domain. It's a double. It's an integral over the domain omega, and we have the functional here as this is our integrand of the function, which is nothing but f. And when we take a look at the expression for the integrand, what we see is there are two independent variables, which are x and y. And there is one dependent variable, z. F is already known here. And oh, sorry, I must call it by another name. Let me just call it as g. So we have two independent variables and one dependent variable, and f of xy is something which is all non a priori. As usual, our process is to first determine our Euler-Lagrange equation. So the Euler-Lagrange equation is del g by what I'll do is I'll take it as d by dx of Dow. Actually, I just keep on using the term interchangeably, but I hope you understand it from the context, whether it refers to ordinary differentiation, I mean, ordinary derivative or the partial derivative. So it's Dow G by Dow Z subscript X. This means that it's with respect to, so it's Dow Z by Dow X plus d by, it's not d, actually it's dou by d. Likewise dou by dou y of dou g by dou zy minus dou g by dou z is equal to 0. So this is our equation. So this is our Euler-Lagrange equation. Fine. So this gives us dou by dou x, dou g by dou zx is 2, likewise 2 minus 2 f of xy. Fine. And this gives us, I'll factor out 2 throughout, and we'll have this is nothing but I'm sure you know this expression very well. You must have come across it. It represents various phenomena such as even steady uh, heat diffusion in 2 dimension. And yeah, so that's one of the one particular phenomena that it tends to model. And it has name. It has also a name on of its own. I'm sure you must be knowing the name. It's known as Poisson equation. Now let's pick up another equation, another question in this series. So is obtain the extremizer of the functional, and we are given a functional here in terms of uh, the independent variable is phi, and the independent variables are x and y, and the dependent variable is phi. Okay, so and since since it's very clear from the expression here that uh, the terms are all the terms are second order derivatives. First, let's determine or let me just let's obtain our Euler-Lagrange equation. And the first term would be here is, I'll just call it the functional here, or the integrand of the functional as f. Let me just call it f. So the Euler-Lagrange equation is dou f phi minus dou by dou x dou f by dou phi x. You must know that, we must knowing that I'm just referring to partial derivative of some quantity with respect to the independent variable as subscript. So it's phi x here, and minus dou phi by dou phi y plus dou square dou x square dou f by dou phi x, second derivative. So it's just let me just verify it. Yeah, it's a single derivative fine. Plus square by dou dou by dou 0. Fine. Now let's recall here that dou phi dou f by dou phi is 0 because there are no terms in just phi. So you have 0 minus likewise to 0 again, 0 again, and dou phi by dou phi xx is 2 phi xx dou square by dou x is 2 phi xy and plus this is given 2 y 0. Okay. That you already recall here is I have made a slight mistake here. It should be 2 into 2, it's 4 actually. Fine. Let's factor out 2 and just dump it on the right hand side. So we have a term of say, let me write it in the full expression here, plus 2 plus I'm sure anyone who has studied solid mechanics should recall this equation, right? So this is nothing but what we call as biharmonic equation. This biharmonic equation. This comes in many forms. It's known by various names, especially in mechanics. In say when we are studying or dealing with plane stress and plane strain problems. Plane stress and plane strain problems. Solid mechanics. Solid mechanics. An equation which tends to one equation which we solve is Airy's equation, isn't it? For which we have something known as Airy's function, Airy's equation, which is a biharmonic equation whose solution is Airy's function. Just to give a background of where we see such equation. Now let's come to another problem in this series. So this problem is of determining the extremal of the functional j of u as a function of x, y, z. This is defined over a domain omega, and need to find how many independent variables are here? 3, which are x, y, and z. And there is just one dependent variable, which is u, isn't it? Fine. So let me first determine the Euler-Lagrange equation in this problem. Okay, so let me call the integrand here as g. Fine. Let me. So we'll have a Lagrange equation. The form will be as del by del x. So dou by dou x of dou g by dou ux plus dou by dou y of dou g by dou uy z of dou z minus dou g by dou u is equal to 0, isn't it? Fine. So this implies that dou by dou x, dou g by dou ux is nothing but 2 dou ux, 2 ux, and we have 2 uy, 2 uz minus dou g by dou u is 2f x, y, z equal to 0. Fine. So this means that we have u double x plus u double y. I'm just filtering out u throughout, factoring out u, and I'm left with 2xx plus 2yy plus 2zz is equal to f. Now, you may also recall the expression here. I'm sure you must have come across this. This is nothing but one example or one phenomenon which it models is heat diffusion in a three-dimensional space or in a three-dimensional domain. And there is also Poisson equation. The previous Poisson equation was in is Poisson equation in 2D, and this is Poisson equation in. I don't know whether it. I'm sure it is known as Poisson's equation in 3D. Likewise, even in this case, it should be Poisson's equation. Fine. Okay. Okay. So the next two problems I had discussed in the previous tutorial session. I'm just going to revisit it because what I say is this problem were more suited to this particular tutorial session. So let me just revisit it. So this is a problem, as I had mentioned in the previous tutorial session, was that there's a problem, in structural mechanics or structural dynamics. Sorry, it's in structural dynamics, and the schematic here shows that we have a mass m which is attached to a spring, which is further attached to a fixed wall, and this mass m is placed on a frictionless surface, and given some initial disturbance or initial perturbations or initial some displacement to the system, it will keep on oscillating, and this system is also called as simple harmonic oscillator. So our aim here is to determine the equation of motion for the system. Right? And mind you that the displacement x here is a function of time t. So now let's first construct, so to speak, a functional for this to derive the equation here. So we have functional as j of x is integral over t from t1 to t2 of the integrand L as a function of t, x, and x dot. And dot refers to differentiation with respect to time. Fine. So let me first construct a Lagrangian here. And I'm sure we had, professor had explained a bit about Lagrangian in his in week 3 lectures. So I won't be going back to. I will not be actually explaining it to what it means, but I'll just expressing the terms, or in terms of how this Lagrangian is expressed in terms of kinetic and potential energy. Fine. So L is defined as T minus V. T here is the kinetic energy of the system, and V is the potential energy of the system. Now you recall very well that kinetic energy is defined as half into mass into the velocity of the mass squared, isn't it? And in this case, the potential energy is stored as strain energy in the spring, isn't it? So and strain energy in the spring when it's say subjected to or when it is elongated by a quantity x, then the strain energy is stored in the spring is half kx squared. So the Lagrangian here is half mx dot square minus half kx squared. Fine. Let's derive our Euler-Lagrange equations. So Euler-Lagrange equations is d by dt of, now here d by dt is the not the ordinary derivative, and of dou L by dou x dot minus dou L by dou x is equal to 0. So this implies that d by dt of mx dot minus kx is equal to 0. So this means that since mass is constant for our system, so we have an expression, we have a final equation as mx double dot plus kx is equal to 0. And this equation actually explains the motion of a spring mass oscillator. And also there's a very well-known equation in structural dynamics of a 1D undamped oscillator. Fine. Now what we do is let me, this was just a background to build up, which was required to, what do you call, to study a system in consisting of two masses and two springs. And we have this, and our goal still remains to determine the equations of motion for the vibrating system. So masses are m1 and m2. They are attached to two springs, k1 and k2. K1 is fixed to the wall, and the corresponding displacement of m and 2, m1 and m2 is given by x1 and x2. So, and when we take a look at the functional here and the integrand of the function, so to speak, we have two dependent variables, which are x1 and x2. However, there is just one independent variable, which is t. So the Lagrangian here that we are going to construct is L is equal to t minus v. So as far as we can recall, this is case 2 of the generalized Lagrange equations that we had revisited in our discussion of theory part. So let's first express our find or derive an expression for the kinetic energy of the system. So kinetic energy is sum of the kinetic energy of both the masses. It's that simple for our case actually, because this is a linear system. I won't be discussing any further on this, but I must tell you that we are discussing a linear system, fine. So t is equal to half of m1 into x dot squared plus half of m2 into x dot 2 squared. And now to derive the expression for strain energy of the spring, here we need to be a bit cautious, because as far as the spring K1 is concerned, it's one end of the spring K1 is attached to a fixed wall. However, the other end is free, so to speak. That elongation will take place on the right hand, on the right end of the spring, and the extension will be given as K1. So the potential energy or the strain elastic energy stored in spring K1 is half kx to 1 squared. But for spring 2, we need to actually be very careful. What we see is the spring K2 has two ends. One end displaces by an amount K1, and the other end displaces by an amount K2, or x1, and the other by x2. So you know very well that the strain energy stored in a spring is proportional to the net elongation or net elongation of the spring. So net elongation is given by kx2 minus x1, fine, or x1 minus x2, as you say, whatever, but it should be a positive. Uh, since energy doesn't care about x1 minus x2, x2 minus x1, so we can express otherwise. So the next net extension, so to speak, is k1 minus k2, fine. And so the strain energy stored in the spring K2 is half K2 x1 minus x2 squared. Okay, so let's go on to discuss the Euler-Lagrange equations. So the Euler-Lagrange equation so we'll have since we have two dependent variables, we will have two Euler-Lagrange equations. So the first Euler-Lagrange equation is d by dt of dou L by dou x1 dot minus dou L by dou x1 is equal to 0. Fine. So this implies that dou L by dou x1 dot is d by dt of m1 x1 dot minus, and dou L by dou x1 is minus k1 x1 minus k2 x2, and x1 minus x2 is equal to 0. And this, since our masses m1 and m2 are both constant, so in the differentiation operator we can always bring it out. So this implies that We have m1 x1 double dot plus a k1 x1 plus k2 x1 minus x2 is equal to 0. And likewise for the second expression, we have d by dt dou l dou, dou l by dou x2 dot minus dou l by dou x2 is equal to 0. So this implies that we have d by dt of m2 x2 dot minus of k2 x1 minus x2 into minus 1, and upon rearranging it we have m2 x2 double dot plus k2 x2 minus x1 is equal to 0. Okay, so let's rearrange it, and we have m1 x1 double dot plus k1 plus k2 into x1 minus k2 x2 is equal to 0, and m2 x2 double dot minus k2 x1 plus k2 x2 is to 0. There is one very elegant way to write this expression, to write the set of equations, and we can write them in something in this matrix form. And so we have m1, so this is known as our mass matrix. This is our mass matrix. And there is our acceleration vector, and this is our stiffness matrix. Fine. And this is our displacement vector, and this is our acceleration vector. Fine. You can also write it in very simple, in a compact form as something called m x vector double dot plus k x vector is equal to 0 vector. Mass matrix, you can represent it as m x different matrix. And you very well recall that x1 x vector is given by x1 x2. Fine. 0 vector is nothing but 0 of it's a column vector consisting of 2 zeros. Okay, so let's move to the third basket of the set of the problems that we had started with. So this problem here is about determining, it's a given a functional of f of x, so f of y is equal to this is our functional function here. I mean the integrand here, x cubed y double prime square plus 100 x square minus 20 x bar. This is defined over a fixed domain of unit interval or interval of unit length, and so we have to determine the extremal y of x which satisfies the condition y1 is equal to y prime 1 is equal to 0, and so we have to use Ritz equation, or Ritz method, with a trial function of the form y of x is equal to c naught phi naught of x. And if you recall that, I mean here our general expression for phi n, and you must recall that phi's are what we had called as basis functions. Fine. So here the general expression for the basis function phi n is xn, x to the power n into x minus 1 whole square. So we are essentially trying to approximate our extremal in terms of just one basis function, which is phi naught of x. Fine. and we have to determine the approximate extremal. So since we already have the expression for our basis function phi naught of x, all that we require is to determine the expression for c naught. Okay, let me do is uh, let me first write our phi naught here. So phi naught of x is x naught x minus 1. So this is given as x minus 1. Now let's check whether it really satisfies. So our y of x will be c naught x minus 1 whole square. So when we put x is equal to 1, then we have y1 is equal to 0, which satisfies the first condition. And the y prime of y prime is equal to 2 into c naught into x minus 1. Again, substituting x is equal to 1 gives us 0. So essentially, as we recall here, is the first basis function, or in this, I mean, the first basis function actually satisfies the boundary conditions. But since the boundary conditions for our case are themselves homogeneous, so we don't need to worry about that. So all the basis functions will satisfy the boundary conditions. So that's what I mean. That's what I intend to say. Fine. So what we do is, um, so this was supposed to be, since we are approximating it, so we'll just call it y. Fine. Okay. So let's take the first derivative, which is y hat of prime is equal to 2c naught x1 x minus 1, and y hat double prime with respect to x is 2c. Okay, so let's substitute the expression for y hat in our functional here, and that's what our goal is, to determine the extremal of this function. So we'll call it as from 0 to 1 x cubed y double prime gives us 2c naught squared plus 100 x, and y hat is c naught x minus 1 squared minus 20 x c naught x minus 1 integrated. Fine. So let's expand it. Set 0 to 1. We'll have 4 c naught squared x cubed plus 100 c naught squared x into x minus 1 to the power 4. Actually, it should be squared here, so it's 4, and minus 20c x into x minus 1 whole squared dx. Let's write this as, let's just break down this integral into different component integrals. We have so c naught is a constant, right? So we'll have 4 into c naught squared, uh, 0 to 1 x cubed dx plus 100 c naught squared integral of x into x minus 1 to the power 4 dx 0 to 1. Likewise, 20c naught integral from x to integral of from 0 to 1 dx. Okay. So evaluating the first integral here is very easy. But for second and third integrals, there is what it's a bit tricky here. The thing is, if we expand our x minus 1 to the power 4, the equation will become really messy. So why not we use a trick? That's what we call as what do you call, changing our variables, isn't it? Or transferring the variable, so to speak. So what we do is, for the second and third expression, let's make some substitution here. Let's call t is equal to x minus 1. Fine. So this implies that we have x is equal to t plus 1. Fine. And this implies that, and at x is equal to 0, when x is equal to 0, t is minus 1. Fine. And when x is equal to 1, then t is equal to, I'll write it neatly. Fine. So at t is equal to, or at x is equal to 0, t is equal to minus 1. At x is equal to 1, t is equal to 0. Fine. And we'll use the substitution in both the first and both in second and third integrals. And one more thing that we can see from substitution here is we can just have dt is still remains as dx. Okay. Fine. Let's move to the next slide to continue this. So this will have as 4 c naught. We had 4 c naught squared, and the integral of x cubed from d to x from 0 to 1. So there's nothing but x to the power 4 by 4 plus, and in the second case we have 100 c naught squared, and the integral is from, integration limits are minus 1 to 0, which we can clearly see from here, minus 1 to 0, and x is t plus 1, and x minus 1 to the power 4 is t to the power 4. And this is dt. Likewise, we have minus 20 c naught minus 1 to 0, t plus 1 into t squared dt. Fine. So 4 into c naught into x1 into so x by 4, x to the power 4 by 4 from 0 time, and then we put the limits 0 to 1, 0 and 1. But the thing is 4 cancels out, so we just have c naught into x to the power 4. At 1 is 1 minus 0. And here what happened is it's 100 c naught squared, and we have minus 1 0, and we'll just multiply. So t naught t to power 4 into t is t to power 5, and t to power 4 into 1 is t to power 4. And similarly minus 1 to 0, and it becomes t cubed plus t squared dt. So this is c naught. It should be squared here. I missed again. Yeah. Plus 100 c naught squared into t to the power 5. This integral is t to the power 6, actually, t to the power 6 by 6 plus t to the power 5 by 5 into 0 minus 20 c naught, and it is t to the power 4 by 4 plus t to the power cube by 3, and it's minus 1 to 0. So we have c naught squared plus 100 c naught squared. But what we look here is that when we put zeros here, then it's just 0 plus 0 minus t minus 1 to the power 6 is just minus 1. And this is because minus 1 to the power 5 is minus 1. So we have minus 1 by 5. Fine. and let's have a proper closing bracket. And similarly, we have 2c naught 0 0 again, so it's just 0 minus of minus 1 to the power 4 is 1 by 1 only, and 1 by 4, and then we have minus 1 by 3. So we are left with c naught square plus, and it's just 1 by 6 minus 1 by 5. Well, this it evaluates to 1 by 30, so it's 100 into c naught square into 1 by 30. Likewise 20 c naught, and this evaluates to 1 by 12. So we are left with c naught squared plus 10 by 3 c naught squared minus, and cancellations with respect to 4 gives us 5 by 3 c naught. Adding the like terms in c naught squared, this gives us 13 by 3 c naught squared minus 5 by 3 c naught. So which means that our functional effectively became a term in f naught. So we can just call it f of c naught. So this is our our functional has converted into, has been reduced to a single variate optimizing problem. Right. So the necessary condition are, and let's just call it as why give it a small f? Let's just call it as, let's just still call it as f of c naught. So necessary condition is given by d of f by dc naught is equal to 0. This implies that this implies that 26 by 3 into c naught minus 5 by 3 c naught of the first derivative with respect to c naught gives us just 5 by 3 is equal to 0. And this gives us 26 c naught. Finally, we have c naught is equal to 5 by 26. So therefore, y hat of x, or the approximated value of the extremal is c naught into phi naught. Sorry, it was c naught into phi naught of x, and phi naught we already know to be x minus 1 whole square. So c naught is 5 by 26. So our extremal is approximated extremal is 5 by 26 of x minus 1 square. Yeah, so this was our last problem to be solved in today's tutorial session. And so if you recall, we started with first solving a problem on basics of arithmetic calculus, then we moved on to solve a bunch of problems in generalized of Euler-Lagrange equations. And then we determined the equations of motion for a vibrating system. We started with single degree of freedom, then moved on to double degree or 2 degree of freedom system. And then we did a problem on numerical solution to Euler-Lagrange equation for a special case, or for just one type, which was Ritz method. And yeah, so with this, I think, yeah, I have this is what I had planned to do in today's tutorial session. So please let me know if you have any doubts. If you would ask me any doubts in the assignment problems, or otherwise, I'm ready to answer any queries that you would have.
I would wait for a few more minutes before. If there are no doubts, then I would be ending our session in a couple of minutes. And mind you that in order to find, say, better approximation for the extremal, we would have to, you can even try it with taking more and more number of terms in the approximation. So in this case, we just took the first basis function, but say if you want a more closer expression for the extremal, then we would be, it would be, it's always, I mean, the procedure is that we take more and more terms of the basis functions, and then, uh, and then if we take a large enough number of terms, we finally converge it in the direction of, or we converge to the analytical extremal for the problem. But what we see is as we take more and more terms, the integration all becomes very messy, and it becomes computationally very involving. So that's always, yeah, there in such numerical procedure. But yeah, so but that's how we define a system. And Ritz method is something which is very much used in say in structural dynamics and all to uh, to obtain the mode shapes for a freely vibrating or diagram for a freely vibrating structure, uh, freely vibrating system, so to speak. Yeah. Okay, so since there are no questions, and I believe that we are left with just just 3 or 4 minutes. So I think I should wind up this session. So we'll have the next tutorial session on a week later on February 21st. So there I would be covering week 3, or sorry, week 4 of the NPTEL course, variation calculus, and yeah. So please let me know if you have any doubts by the next session, in our next tutorial session. So with this, I'm just winding up today's session. Okay, let me stop the recording.